Okay, good morning. All right, so reminder again, exam is this Thursday, 6:30 p.m. Make sure you know where you are going, look up your TA's name, and find the location. Once again, if you're in Alex Porter's class, you're in Lynn Hall, and that's way south of here. It's the veterinarian building. If you've never been there, make sure you find out where it is before the night of exam. Okay? Exam will cover starting from the centroid stuff up to what we're doing today. And we'll do review in class on Wednesday. All right, so today we're going to continue section 11.10. More on Taylor and Maclaurin series. And like I said, exam 3 covers up to this lesson, starting with the centroids, and then all the series stuff, and then the Taylor and Maclaurin series. All right, so first of all, let's do a very brief review of what these two series are. So you remember that the Taylor series looks like this. So we build this series near this point, x is equal to a, and we need a bunch of derivatives. And it looks something like this. You need the nth derivative over n factorial times x minus a to the n, and then that continues on. And then when a is at 0, Taylor series turns into the Maclaurin series. So keep in mind that Maclaurin series is a Taylor series, just a very, very specific kind of Taylor series at a specific value when a is equal to 0. And it's very frequently used, and that's one of the reasons why it gets its own name. All right, so these are things that you got to know for the exam too, for the Taylor series part. And once again, as a very brief review of how these things work, let's find the Maclaurin series of e to the x. Remember, we're going to need the function value and a bunch of derivatives at 0, right? Okay, so f of x is e to the x. F prime of x is e to the x. F double prime of x is equal to e to the x f triple prime is e to the x. That's what's so nice about e to the x. It doesn't change, right? It's the same thing over and over again. Then we need to know what happens at 0 because we're dealing with a Maclaurin. With a Taylor, this could be any number, but Maclaurin, we're always at 0. So 1, 1, 1, 1. This thing doesn't change. Okay, so now the Maclaurin series, remember, we're doing this thing here. The nth derivative over n factorial times x to the n. So what do we see? We see 1 plus 1 over 1 x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus dot, dot, dot. So how would you express this in summation notation? Let's do 0 to infinity. What do you think? Yeah, that's a good idea here. So x to the n, that part is pretty easy. X to the 0, x to the first, x squared, x cubed, right? X to the n is the easy part. Downstairs, think of that as 1 factorial. Think of that as 0 factorial. So when n is 0, we get 0 factorial downstairs. When n is 1, we get 1 factorial, 2 factorial for n is equal to 2, and so on. So there's the Maclaurin series for e to the x. Okay? It's a very nice and very simple series, x to the n over n factorial. Okay, let's try something else. Let's try e to the x squared. If we follow the same procedure here that we did with the e to the x, so that's where we start, right? F prime would be, what's F prime? What do you get when you differentiate that? Right, 2x e to the x squared, right? You got to use the chain rule to do it. Now, how do you get F double prime then? What rule do you have to use? Product rule, right? All right, so let's take one step here. Here's the first times the derivative of the second plus the second times derivative of the first. Stop it. So what do we get? We get 4x squared e to the x squared plus 2 e to the x squared, or e to the x squared times the quantity 4x squared plus 2. Okay, that's not terribly hard, but you see, if you keep doing this, that's going to involve another product rule, and that's going to continue for quite a while. And this process is fine. Nothing wrong with it. But tedious, right? You got to take derivative of this. And you can imagine if the exponent gets more complicated, this stuff might get terribly difficult. Then the question naturally arises, what can we do to make that process easier? We still would like to find the Maclaurin series of this thing, but it's starting to get a little bit difficult to do. Let's find an easier way to do it. And we have seen, we're going to use what we did with the geometric series. Remember, we took advantage of that, and we used that to find something like this by making it fit into that pattern. Right? Remember, we changed the x in here to negative x squared over 2, like that. Okay, remember doing that? Yep. Now we're going to use exactly the same idea to modify the Maclaurin series we have for e to the x so that we could get e to the x squared without having to differentiate a bunch of times. Okay, so first of all, remember we found the Maclaurin series of e to the x. And now we're going to change x to x squared so that we could get a Maclaurin series for e to the x squared. And that x turns into x squared, right? Like that. Oops, x, sorry. So that's x to the 2n over n factorial. Let's write out a few terms for each of them. The 2n here for x as an exponent means all the exponents are going to be even. Starting at 0, we get 1 still. When n is 1, we get x squared over 1 factorial. When n is 2, we get x to the 4th. But downstairs is still 2 factorial. When x is 3, we get x to the 6th power. When n is 3, sorry. And downstairs is 3 factorial. Okay, so now we got the Maclaurin series of e to the x squared pretty easily. And if you actually carried out this process using a definition of Maclaurin series, you would get the same thing. But this would take a little bit longer, and you got to use a little bit more complicated differentiation rules to get it. Does that make sense, this idea? If I give you e to the x and then ask you to find that, you just take advantage of what's given. Okay, let's try another one. Find the Maclaurin series of 2e to the x plus 4e to the 3x. Same idea. Instead of differentiating this a bunch of times and then put it together, we'll take advantage of what we know. If this problem were to show up on the exam, I would give you e to the x, the Maclaurin series of e to the x. By the way, that's a good time to talk about what will be given. You will get a Maclaurin series of these things, e to the x, cosine of x, sine of x, and inverse tangent, if needed. The only thing we will not give you is the geometric series. We will not give you all right, so that one you have to know. You're on your own with that. And the reason is because we studied that for quite a bit. It's reasonable for you to for us to expect that you would know that. Okay, so you get e to the x, cosine, sine, tangent, inverse, if the problem requires you to do something like that. Say that again?
You're saying that those will be given to us, not asked of us.
Right. Right. I'm not going to give you a question asking you to find this and then give you that. That's insulting, right? So I'm going to give you, for example, something like that, but I give you this, and you got to use this to find that. Of course, if you get stuck, you could always do it the regular way, differentiate a bunch of times, and then put it together. That's fine. There's nothing wrong with that process. Okay, so let's put this together here. That e to the x can be directly replaced. And then e to the 3x, we know how to replace that. I simply change all the x's to 3x. Like that, right? Okay, simplify a little bit. Let me bring the 2 into here. Remember, anything that doesn't contain an n, you can bring that directly into the summation or out. You can treat the summation like an integration. All these constants multiplied and divided can be moved in and out whenever convenient. Same thing with that 4. Let's bring that into here. Three gets power of n. Let's separate that out. And x gets a power of n. And downstairs, we get n factorial. Now let's combine them. It's easy when these are the same. When they're both to the same power, so x to the n, x to the n, that's very good. You can just simply combine them into one. But when they're not the same, it gets a little complicated. So for example, I'll just simply add these into one summation here. And also I need to mention, when it's the same n, same starting n, right? Both start at 0. If one starts at 1 and the other one starts at 2, for example, even if the powers are the same, you can't combine directly. But here we got a great situation. 0, 0, x to the n, x to the n. Directly combine them. And then look at this. We see a common factor of x to the n over n factorial. So let's further rewrite this as 2 plus 4 times 3 to the n times x to the n over n factorial. So there we go. Okay? Questions? Nope? Good. Okay, let's try something a little bit different. E to the x is pretty easy and not terribly interesting. Okay, so let's find x times sine of x squared over 3. And you're provided with sine of x is equal to the summation minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. By the way, let's look at what this looks like. 2n plus 1, these are all the odd numbers. 1, 3, 5, 7, 9. 2n are all the even numbers. So these guys have all the odd exponents. And they're divided by the same number factorial as their exponent. And then they alternate signs. Right? So this looks like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7, 7 factorial, blah, blah, blah. So the first step is to take care of this sine part. We have the Maclaurin series for sine of x. That means we can handle sine of anything else. Let's do that part first. Once again, whenever you see an x in the original Maclaurin series, change it to x squared over 3. So here is the change. All right, so here's what we got. Now the best thing to do next is to break this up. We would like to see x to something instead of x squared over 3 to the something. So let's take care of that 3. Move it out of the way. So first we get x squared to the 2n plus 1 over 3 to the 2n plus 1. Oh, let me rewrite this. It's getting too cramped. All right, so here we go. X squared to the 2n plus 1 over 3 to the 2n plus 1. Downstairs is still 2n plus 1 factorial. Then let's bring this 3 to the 2n plus 1 downstairs with 2n plus 1 factorial. And then up here, when you multiply this together, remember 2 goes into here and that. Now the numerator, therefore, is going to be x to the 4n plus 2, right? 2 times 2n plus 1 is 4n plus 2 times 1. And then downstairs is 3 to the 2n plus 1 times 2n plus 1 factorial. Okay, so we took care of the sine part. Now remember, the original thing we're dealing with has an x in the front. We took care of that, right? That's easy. So let's replace that with our infinite series. And that x has a power of 1. It doesn't contain any n, right? So we can just bring it in. And what does it do when it comes in to this x already here? Yeah, you bump the power by 1, right? We're bringing one more power of x into here. So this gets another addition to the exponent. So it's 4n plus 3. All right? So there we go. It's not very pretty, but it is what it is. Let's write out a few terms of this and see what it looks like. When n is equal to 0, this is 1, and this is x cubed. Downstairs, we get 3 times 1 factorial. When n is 1, this will be negative, and this will be x to the 7th, right? And downstairs is 3 to the power of 3 times, what's this, 3? Yeah, 3 factorial. Let's go one more. Why not? When n is equal to, let's see, 0, 1, 2 now. So this will be 8 plus 3 is 11. This is 3 to the power of 5 times 5 factorial. And so on. Okay? Right? So that's what it looks like. Now, this would be terribly difficult to do if you actually go through the definition way, getting derivative, evaluate at 0. This would be very, very complicated. You got to start with a product rule, and then there's another product rule that's going to jump in. It's very, very complicated. But this is a much easier way to get exactly the same Maclaurin series, provided that you know the Maclaurin series of that to begin with. Okay, questions on this? No? Okay, good. Now let's try this one. Let's integrate sine of x over x, sine of x minus x, the whole thing over x. Without Maclaurin series, this is something that you probably would do by integration by parts. Not too difficult, but it's an involved process. Now let's see what happens when we turn this into a Maclaurin series and then integrate it. Same idea here. Going to use the known Maclaurin series and then put the whole thing together and then integrate. Right, so this is actually a two-part process. We've got to do the numerator first, then the denominator, put it together, and then we integrate that. So this thing here, as you can see, it's not very easy to take care of in the summation form. It's not clear when I bring this into here what would happen to that. It's not easy to simplify. Okay, that x comes into here, what happens to it? Not very easy to see that. So what you're going to do here is to write out a few terms of this thing. Subtract x, and then put together a new summation, or you can divide by x and then do that. So that's the idea here. All right, so this, remember we saw this earlier, alternating signs, x to the odd powers divided by odd factorial. First one is 0, so we get just a 1. And then all the odd powers divided by the same factorial downstairs. Oh, I'm missing something. I'm missing. So 1 is, okay, 1 is good. Minus x, right? That's my first one. And then this is, rewrite. Okay, let's start with 0. 0, I get my 1. When n is 1, no, I don't start with a 1. What am I doing? When n is 0, I get positive x, right? Positive x. When n is 1, I get negative x cubed over 3. When n is 2, and all these dots. So this is the summation stuff. The summation turned into this thing right here. And then I'm subtracting an x. Right? So you see what happens here. The first term gets taken away. Everything else is staying the same. Right? So the first term goes away, so this new thing here starts at negative 3, negative x cubed over 3 factorial. And then the same pattern, alternating signs. Right? So how would you express this in the summation notation? Look at the summation for sine of x, and look, what did the subtraction of x do? Yeah, exactly. It took away the first term. So it's as if my series starts one term later. It's exactly the same thing, but we start at 1 instead, since we lost the first term. Do you see that? Make sense? Okay, so that's what it's going to look like. Is that the only way to write it? No. How many different ways can you write it? In principle, infinitely many different ways, right? But that's probably the simplest way to write it. We did that by removing the first term of the series. Okay, we may or may not need it, but it's there if we find it useful. All right, so then we'll take care of this. And this seems pretty easy if we look at the terms one by one and divide it by x instead of dealing with that, right? So this is fine, but this seems a little bit more straightforward to deal with. So we take all of these guys, divide every single one of them by x. So notice the powers turn into even numbers now, since we're subtracting 1 from each one. Okay. What did I do? 8. 8. Oh, 9. Only different by 1. Big deal. Yes, big deal, actually. Okay, x over 8 over 9 factorial. There we go. Okay. Okay, we could write out a new summation if we want, but we're going to integrate that. This is easier to integrate than this thing here. Let's just integrate first and then collapse back into a summation. Okay, integrate term by term. So now, this is one of the major advantages of dealing things in power series form. These are easy to integrate. No fancy rules, just a good old power rule. Things like that are hard to integrate. This is one of the major advantages. All right, so let's do that. We get negative x cubed over 3 times 3 factorial plus x to the 5th over 5 times 5 factorial. And the nice thing here is the pattern is very, very clear. Power, number, number factorial. Flipping signs everywhere. So what did I do? Here, this guy. X to the 7. 7 times 7 factorial plus 9, what else? 9 factorial, negative dot, 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 plus c, right? I'm integrating, so I get a plus c at the end. Okay? All right, now the summation part here. Remember, you could start anywhere, but one thing we note is back here, by taking away this, we basically started a series we started with one term later. So it's a good idea to stick with what we had, starting here at 1, and then 2, 3, 4, and so on. It's easier to handle that way. And also, it's easier to relate 1 to 3, 2 to 5, 3 to 7. It's fine to start at 0, but it may be a little bit more difficult to put things back together. All right, so now I want you to take 1 minute and give me a summation of this thing here. The C, you can leave it out for now. So here's the starting, and I want a summation notation. 1 minute. If this problem is on the exam, that's all the time you got, 1 minute to put this together. It might take you, so each problem you have on the average of 5 minutes to do. 12 problems an hour, right? So it probably would take 3 to 4 minutes to get here. Now you got 1 minute to put this together. And go. Okay, close enough. What do you got? Okay, do we agree with this part? Good. Okay, what's next? X to the 2n plus 1. We agree with that? Good. Downstairs?
Divided by n times n factorial.
Say it again?
Divided by quantity 2n plus 1.
Good.
Times quantity 2n plus 1 factorial.
Excellent. We got that? Good. What else is here? Yeah, so plus c, okay? So there we go. It's a complicated looking series, but what we did is we accomplished the integration without having to use anything fancy. And if you want to write out a few terms, we already have that. Okay, one last example. Okay, remember when you took Calc 1, you saw this limit, and before you had L'Hopital's rule, you had to take it. You could prove this using geometric ways, or you just had to accept it. Now, L'Hopital's rule would give you a 1. Now we're going to use series to show that it is indeed a 1. And once again, we're going to start with this sine series we've been staring at. And just write out a few terms of that. X minus x cubed over 3 factorial, and so on. Good. Then the series for sine of x over x. And we know how to do this now. We just divide all of them by 1x. So there's my 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus dot, dot, dot. Okay, now it's obvious when you take a limit, letting x go to 0, this guy goes to 1, right? Obvious. That goes to 0. That goes to 0. All of these dots contain powers of x greater than 1. So all of them go to 0. The only thing that's not affected is this thing here. So there you go. That's another way to prove that that limit, indeterminate limit, does turn out to be 1. All right, that's it. See you on Wednesday.
if the series comes out to be true, for example, if I add something and subtract something else, that's going to be like the final series. So, therefore, the series still going to x goes to the limit of x going to 0 It's true that if x goes to 0, then the division is alpha, but it doesn't go to 0 because it goes never goes to 0. That's the idea of limit. We don't let go.
When you put the limit x approaches 0, oh, okay.
That's what we do. It doesn't matter even if it goes to infinity. The series converges regardless of the number of series. The sine series converges with any number of different infinity, that's a big number, still goes to converge. What if it's careful with the concept of the convergent series and the number itself, the number of x. Think of the geometric series. I'm going to ratio to think -1. You think convergence. It doesn't matter what number you put in there for that x.
So simply consider infinity itself, which is really large.
Infinity is for that number of x. That's nothing to do with the series. And the series converges. The series is what the series is.
But it converges to 0. So it
Converges
converges to the value of what that sum is, and while it vary based on what the value of x is.
That's correct. But it doesn't change the integration. It converges or diverges